Section 1.4, Approximate Linear Relationships. In the previous section, we looked at relationships that were exactly linear. In this section, we're going to look at ones that are a little bit more realistic, where we have a roughly linear pattern, but not a perfectly linear pattern. Let's look at an example. The percentages of Americans who currently have a personal profile page on a social networking website such as Facebook are shown in the table below for various age groups. Let P be the percentage of Americans at age A years who have a personal profile page. Draw a scattergram for the data by hand and use the grid provided, and also allow room for the ages from 0 to 120 years old. So if we hadn't got this bit of directions, we probably would have started from age 0 anyways, but the 120 is something we probably wouldn't have done. We would have just worried about fitting the 70. They'll ask us to do that sometimes, especially if they think that some of the predictions we're going to make are going to fall out into that range. Alright, so let's go ahead and look at the data set. We've got the age groups from 12 to 17, 18 to 24, 25 to 34, and so on. And you can't really plot a group like that. So what they do in a case where you're given a range is they use the average to represent that value. So even though the first age group is people from as young as 12 to as old as 17, we're going to kind of pretend they're all 14.5 for the purpose of graphing it. And that 14.5, they're getting it for us, but it just comes from averaging these two values. So instead of using this for our variable A, which we can't really do because it's ranges, we're going to use this column right here for our variable A. And then these are going to be our percentages. And as is typically the case, the first column will be our independent variable and the second one will be the dependent. So these are going to go on the horizontal, this will go on the vertical. So the first thing we need to do for the scatter plot is come up with a scale. So let's draw in our axes. Because all the values are positive, which is typical for these real life applications, we're going to put everything in quadrant 1. So our horizontal will go on the bottom and our vertical will go on the far left. And then just remind ourselves of the variables. So our input variable is going to be A, so that'll be here. And the dependent is going to be P, so that'll be here. Alright, so now we want to start deciding on the scale. So first we'll do the horizontal, which is the ages. Since 14.5 is closer to 0 than to 70, we'll start at 0. And then normally I'd say let's make sure that we pick a scale so 70 fits, but they told us to allow room for 120, so we need to make sure that fits. So the process there is to take that maximum value that we're going to graph, 120, divide it by the number of squares, which we could count out, and there are 14 of those. We get 8.57, so we want to round that up to something nice. So 10 makes sense. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 110, 100, 110, 120, and 130, 140, but we probably won't need those. And then we want to set up the vertical, and 13% is closer to 0 than it is to 78, so we'll start at 0 on the vertical also. And similar process, we'll bring in a calculator, take our maximum number, which is that 78, divide it by the number of squares, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and round that up to something nice, and I think 10 makes sense. So 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100% in case we need that. And we've got our scale taken care of. Because the numbers are so similar on both sets of axes, I'll go ahead and label these two. So this is age and this is percent. Hopefully that'll help us keep them straight. And then we're just going to start plotting those ordered pairs. So 14.5 and 78. 14.5, roughly halfway between 10 and 20, so I'm going to go about halfway. And up to 78, this is 60, 70, 80, so 78 would be right about there. Then over to 21 years old and up to 77%, so just past the 20 and just a tiny bit below our 78 from a moment ago. Over to 29.5 and up to 65, So 60, 70, 65 would be halfway, and just short of the 30 mark for the 29.5. And you can see already our pattern is not perfectly linear this time. Over to 39.5 up to 51. So just above the 50 mark and just before the 40-year-old mark. 49.5, 35. So there's 50. And 35 would be right about there. And then 59.5 and 31. And finally over to 70 and up to 13. Alright, so there's our plot. And I'm going to skip over B for a moment here and answer the question on part C. Are the variables t and a linearly related, approximately linear related, or neither? And I believe this should have said p, so I'll fix that for you. So are the variables p and a linearly related, approximately linearly related, or neither? So we would only say linearly related if it was a perfect line where you could draw a line and it would hit every point dead center, so you wouldn't have this kind of bumpiness to it. We would say neither if we didn't see a pattern at all, but this seems to be approximately linear related in the sense that I can take my linear pen and lay that across there and all the points are covered up. So it's not perfect because I couldn't draw a line that would hit everyone, but it's roughly linear in that they're all close to that line. Now let's fill that in. Alright, and then let's go ahead and bounce back up to part B now. Alright, in part B they want us to create the same scattergram using the graphing calculator, and we're going to start that out by writing the appropriate window settings below. So one of the things that you have to do on the graphing calculator when you're doing a plot is decide how to set up your window so that it would match what we did over here. So x min is the smallest number on your horizontal axis, which would be the 0. The x max would be the largest on the horizontal max, or horizontal number line, so 120, 130, 140. And then the scale is how much each square was worth, so we went 10, 20, 30, so we were using a scale of 10. Then we do the same thing for the vertical. So the y min is the smallest on the vertical, which is 0. The y max is the largest. We only numbered 90, but it went to 100 and 110. And then the scale, we use the same scale, 10, 20, 30, so going up by tens. So there's our window settings. And now we're going to want to bring in the graphing calculator and transfer all this information there, but also get all the data in there, so I'll show you how to do all that. Alright, so the first thing that we want to do is get the data put into the calculator. So bring that in, and then we're going to start out by hitting the Stat button, and then Edit will already be highlighted, and we want to choose that. And we want to put this first independent variable column into list 1, and the dependent variable column into list 2. I already have some data in there, so I need to clear that out. The way you do that is you highlight the list header, like L2. You hit the clear button, which doesn't seem to do anything, but down here it's saying L2 is going to be blank. If you press the down arrow or enter, that'll accept that. So one more time, go to L1, so we're highlighting the column name. Hit clear, which will set that to nothing, and then press the down arrow or enter, and it'll erase it. Then we want to type these new numbers in there. And once we've got all of those in, I just press enter after each one. Use the right arrow key to move over to list 2, and then let's put those percentages in there. Again, just pressing enter after each one of those numbers. So we've got our data in. Now we want to make sure that we have the plot set up the way we want it to be. So above the y equals key, it says stat plot. So I'm going to hit second to get to that blue. I'll hit the blue key, so second, and then stat plot. And I'm going to look at plot 1, so it's already highlighted, so I'm just going to press enter. And I want it to be on. And then the type that I want is a scatter. So we have these 6 different types of graphs. The only one we're really going to use this semester is the Scatterplot. And you want your X list to be L1, your Y list to be L2. If they're not, you can change those by selecting these lists above the keys. There's in blue L1, L2, L3. So if I wanted this to be list 3 for the Y list, I would hit second and L3. But I do want list 2, so I'll change it back. And then typically when people do graphs, they just use a little dot to mark the points, but it'll show up better if you use the square, so I would recommend setting it that way. Alright, so the plot is on. It's a scatter with the lists in L1, L2, and plotted with the square. Alright, so we're almost there. Next we want to hit Y equals to see what's going to be graphed. We have plot 1 highlighted, which is good because we want to plot it, and then the Y1, Y2 is empty, which is also good. If you had something in there like this, just go to that Y1 equals, Y2 equals, whatever has stuff in it, hit clear, and just get rid of that. Now, if I just hit graph, maybe I'll see the plot, maybe not. So let's see what happens. Looks like I'm getting kind of an empty window. And the reason for that is I'm just graphing kind of whatever window was set up last. But I need to make sure it's a window that shows the data, and we already decided what would do that right here. So now we just want to make that match. So we hit the window key. And then for the X min, I'll put 0. For the X max, 140. And the scale is 10. The Y min is 0, the Y max is 110, and the scale for the Y is also 10. The resolution I never mess with, so I just recommend leaving that alone. And if we hit the graph key now, we should see this duplicated on the screen. And there it is. So drawn a little bit more precisely, but it still looks like essentially the same graph. So that's the process. And it's faster to do it here. It takes a little getting used to. But one of the nice things about this is you can make quick changes. Like they wanted us to put age of 110 on our graph, so we ended up going all the way to 140 because of our scale of 10. But we could change that to something like 80 and see our data spread out a little bit more. Our highest percentage only went to 78 and our graph went up to 110. So we could change that to something like maybe 85. And then we see the data spread out even more. So it's nice to have it on the calculator because it's so quick and easy to make changes. All right, I'm going to go ahead and set it back to what it was to match this. And there we go. All right, let's see what's next. So in part D, they want us to draw a line that comes close to the points on the scatter plot. This is a part that can be frustrating for a lot of people because we may not agree on this. But there's no one perfect line that goes through all these points because our data set is not perfectly linear. So what I want to do is just get my ruler lined up in a way that seems reasonable. I'm not trying to hit any specific points. Sometimes people think you should go for first and last. But you know, if you start lining up different points, you get a lot of really different lines. So just try and pick something that goes through the center. Some points above, some points below. Again, not really specifically targeting any point, and then draw a line. Again, the frustrating part for people is maybe your line's going to look a little bit different than mine, but as long as your line goes through the middle of your points somewhat like mine did, it's okay. Alright, so now we're going to use that model to answer some questions. So use your model to predict the percentage of 25-year-old Americans who currently have a personal profile page on a social networking site. And was this an interpolation or extrapolation? Explain. So first let's just make the prediction. So this 25-year-old right there, that's an age, so that would be a value for the variable A. So I'm going to want to go onto my graph, go to 25, right halfway between the 20 and the 30, go up until I hit the graph, go across, look at the age, or the percentage, sorry, it looks like that percentage is 70%. Again, your answer might be slightly different because you didn't draw exactly the same graph as I did, and when you're using your own model that you drew in, you should put whatever you get from that model, even if it's a little different than mine. And then was this interpolation or an extrapolation? So we'll define those on the next page, but an interpolation is when the x value or horizontal value they give you is bigger than your smallest and smaller than your biggest. So what I mean by that is a 25-year-old's older than 14 and a half but younger than 70, so it fits within the range of this data set. When that happens, that's called an interpolation. If it had been younger than the youngest or older than the oldest, then we called it an extrapolation, and we're about to see one of those. As next, they ask us to use the model to predict the percentage of 3-year-old Americans who currently have a personal profile page on a social networking site. So same idea. Go to our graph. Here's 0 years old, here's 10. So 3 would be maybe somewhere around here. We just go up until we hit the graph, go across to see where that is. Seems about halfway between 90 and 100 on mine. So I'm going to call that 95%. And then when they asked me the question of was that an interpolation or an extrapolation, because the 3-year-old was younger than the youngest in the table, left to all of my data values, that would be an extrapolation. And the same thing would have been true if they asked for like an 85-year-old, which would have been above the 70. So that's an extrapolation. And that's because it was outside of the age range, outside of the given age range. It's not outside of my scale, but it is outside of the ages that were given, and we can give the same type of explanation for interpolation. It was within the given age range. And one of the key reasons we want to think about that is interpolations are more trustworthy than extrapolations when it comes to making predictions. We have a roughly linear pattern to our data set, but we don't know if that pattern continues forever in both directions, and a lot of times it doesn't, and the more you get away from the given range, the less reliable those predictions are. So saying that 70% of 25-year-olds are on social networking site is probably reasonable. But if you look at this prediction down here that 95% of 3-year-olds are on, doesn't really make a whole lot of sense. And it's not surprising that you get a bad prediction when you're extrapolating. So we try to avoid extrapolating, and if we do it, we always take those predictions with a grain of salt, knowing that they can be off by quite a bit. So let's define those terms that we got on the previous page. We had interpolation and extrapolation. So an interpolation is when we make an estimate for a dependent variable, which is our input or horizontal variable, using a value of the independent variable that is in the given range of the independent variable. It doesn't have to be a value that was in your set, but it has to be, again, bigger than the smallest and smaller than the biggest, so it fits in between the min and max of the set. An extrapolation, on the other hand, is when we make an estimate for the dependent variable using a value that independent variable that's not in the given range. So in the example we just did, it would be younger than our youngest or older than our oldest. And one of the reasons we want to think about this is it's common when we do extrapolations that the model breaks down. And that's when a given model, when a model gives a prediction that does not make sense or an estimate that's not a good approximation, we say that model breakdown has occurred, and this is most likely to occur when we try to extrapolate. Which is why we try not to do that too often, because we know there's a danger of getting bad predictions or model breakdown. Let's go ahead and look at another example. The numbers of ride-related injuries at fixed-site amusement parks are shown in the table below. Let n be the number in thousands of ride-related injuries at fixed-site amusement parks in the year that is t years since 2000. Draw a scattergram for the data on the grid and allow room for the year 2028. So as we've seen in previous problems, when they give us the year, that's usually not our input variable. They typically assign t to be the number of years that have passed since some fixed date, and in this case they're fixing that date at the year 2000. So we want to think about in the year 2002, how many years had gone by since 2000. So this is 2 years later. 2003 would be 3 years later, 4, 5, 6, 7, 8, 9, and 10. did this really fast because these were going up by 1 each time. These had to go up by 1 each time. But really all I'm doing is a subtraction. So 2008 you could get all by itself. 2008 minus the starting year of 2000. And there's our 8. So these are subtractions, but whatever pattern you see on the left, like going up by 1, will hold over here as well. Okay, so that's going to be my horizontal variable t. And then what letter did they use for the other one? N for the number of injuries, so that'll be here. And those are going to make up my ordered pairs. So we want to go ahead and do a scattergram for that down here on this grid. And they're all positive numbers. So we can use the far left and the very bottom. So drawing my vertical axis on the far left and the horizontal across the very bottom. Again, kind of nice to have a clear ruler to help line these up better. And then this is the horizontal, so it's T, and the vertical on this one is N. And then we need to start thinking about scale. Normally we'd just say let's make sure this year 10 fits, but they said to make room for 2028, so that's what we're going to focus on. So 2028, got to back up here a minute. So 2028 is not our data value, but the t that would go with that would be 2028 minus 2000. Don't have much room to write, so let me just calculate it here. 2028 minus the 2000 is t equals 28. So when they say to make year for the room 2028 on a grid, that really means make room for t equals 28. And we have let's count those out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 squares in that direction. So 28 divided by 14 means we should use a scale of 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And then we'd have 26 and 28. So that 28 is just barely going to fit on there. And it just barely fits because I didn't round this up at all. But you don't have to round up. It's just when these are messy you want to. That came out nice, so I just used the 2. On the vertical, let's see, 1.3 is a little bit closer to 2.5 than it is to 0. So in cases like that, I would normally make a break in scale. And in fact, I almost did it. But here's the thing. If you look at the pattern, these are getting smaller. And these are getting bigger. So when we do something with a t equals 28, that's a lot bigger here. So we're kind of going farther down this list. These are going to keep getting smaller. So in order to have room to make this prediction, I better put the 0 as a starting point on my grid. So I'm going to do that. I'm going to start at 0. So let's think about the scale then. Take the max, 2.5, divide by the number of squares, which is 11 if you count them out. So here's what I get. Use a scale of 0.227. Well, that's pretty messy. So how about 0.25? So 0.25, 0.5, 0.75, 1.00, 1 1/4, 1 1/2, 1.75, 2.00, and then 2 1/4, 2.5, 2.75. So that'll fit, and we'll have room to go all the way down to 0 in case we need that for the predictions related to t equals 28. All right, so let's start with our plot. Over to 2, up to 2 1/2, over to 3, and we were numbered in 2, so we've got to go halfway in between. So over to 3, up to 2, over to 4, up to 1.6, and that would be, let's see, we did 1 1/2, so 1.5 is here, 1.6 maybe right about there. A little closer to 1.5 than it would be to 1.75. Over to 5, up to 1.8, so we got kind of a bounce back there. Over to 6, also 1.8. Over to 7, down to 1.7. And 8 was a 1.5. 9 is 1.2, This is 1.25 and this is 1, so just a little bit below the 1.25 mark. And then for 10 we're up to 1.3, which is just a little bit above the 1.25. So there's my scatter plot. Roughly linear, kind of. Not as good as the last one, but still kind of. Not a real strong pattern, but there is something roughly linear there. And they want us to draw in a reasonable model like they did before, so I'll go ahead and do that. Just a little bit of a wrestling match this time, because you're like, here's most of the data, so you want to do something like that, but then I'm ignoring this value, but on the other hand I don't want to swing all the way up to that because it gives it too much weight. So maybe something about like this. And it goes kind of through the middle. We have several above, several below, so we probably did okay with our linear model. Yours might be different, that's okay. There's not just one perfect model when you're drawing it by hand. We will get to that in later chapters where we have a mathematical way to figure out the best model. Here we're just trying to get something that seems reasonable. Now if we want to duplicate this on the calculator, then our x min would be the left hand side, 0. The x max would be the right side, which isn't 24, but 26, 28. And we are numbering in 2s. And for the vertical, we started at 0, went up to 2, 2 1/4, 2 1/2, 2.75, and we were doing 0.25 for each square. So we'll want to set that as our window. And we're going to want to put the data in, all those sort of steps that we did on the calculator, just like on the previous couple pages. So bringing in the calculator again, let's go ahead and get our data in there. So I'm going to press the Stat button. Edit is highlighted. I'll press Enter. I have the lists from the previous example, so I'll clear those out. Remember, that's highlight the list, press Clear, and then down arrow. I'm going to enter these into L1 and these into L2. Alright, so I got all those entered in, and then I want to make sure that the window matches up with what I have over here, so I'm going to press the window button. And I'm going to go from 0 to 28 numbering by 2s, and from 0 to 2.75 numbering by 0.25s, and again, don't mess with the resolution part. Check your y equals to see what you have set up. We're going to graph our plot, and no equations, so that's perfect. So let's bring that over here. Press graph to make that happen, and hopefully that looks kind of like what we have here. And I would say yes, we use dots instead of squares, so some of theirs look a little bunched up where ours are separated, but it is essentially the same graph. Alright, so let's see what else they have for us. Drawing the linear model we did already. What is the n-intercept of the model? What does it mean in the situation? So remember, the intercept is where you cross an axis. They want the n-intercept, so where we cross the n-axis, right here. Now again, you should put whatever you have for your graph. For me, that n-intercept is over 0 and up. It looks like it's probably hitting that notch, so that'd be 2 and 2 1/4 and 2.5. So over 0 up 2.5, and again, yours might be different because you drew a different line. Put whatever right here that you see is the height right there on your graph. And then to think about what it means, let's throw some units on there. 0 was t, which was years, so 0 years. And 2.5 was the number of injuries in thousands, so 2.5 thousand injuries. And then we just want to put that into a sentence. So 0 years, we don't want to ever really say 0 years since 2000. If it's 0 years since 2000, we're talking about the year 2000. So I would say in the year 2000, and then I've interpreted this part, the number of injuries, and you could go a little bit longer With this, you could say the number of ride-related injuries at fixed site amusement parks. I think saying the number of injuries is relating it back to the application good enough. The number of injuries is predicted to be, and 2.5 thousand. What you want to do there, instead of saying 2.5 thousand, take 2.5 and multiply it by the number 1,000 in place of the word 1,000, and then it's 2,500. So in the year 2000, the number of injuries predicted is 2,500. Now, this is an important word. It's the number of injuries predicted. This is just based off of the model, which I drew. It's not based on the real data. So we're not saying that's what it was in 2000, but if you forced us to guess, that's what we would guess based on our model. All right, and then what is the t-intercept and what does that represent? So let's have a look at that. The t-axis is our horizontal one, so the t-intercept would be right here. And what is that ordered pair? So it kind of seems like it's hitting in the middle right there. This is 16, 18, and 20. So it looks like t is maybe about 19. Let me actually stick with the purple there. So t is 19, and then the vertical on that is 0 because we're on the horizontal axis. So just following the pattern of up there, that would be 19 years and 0.0 thousand injuries. So kind of an interesting thing we're predicting here. We seem to be predicting that 19 years after 2000, which would be in the year 2009, there would be no injuries. So the model predicts that in the year 2019, and that just comes from taking the 19 years and adding that onto the starting year of 2000. So the model predicts that in the year 2019, there will be no injuries. So two ways to think about that. One would be, if you're afraid of roller coasters, wait until the year 2019, and then there will be no injuries that year, so you don't have to worry about it. The other way to think about that is that that value is outside of our given range by quite a bit, and so you would expect it to be likely that there's model breakdown. So the number of injuries are going down, but do we really think that in a few years there'll be none? Probably not. So I would expect that that is actually not going to happen, but will represent model breakdown from us trying to think about what's going to go on outside of our given value range. Now this prediction is an extrapolation too, but if you look at how far to the left we are from our nearest data value, it's not that far compared to this. The further your extrapolation, the more worried you would be that the model would break down. So I'm not convinced this is right, but I trust that one a little more than I do this one. All right, we have a follow-up question here. Use your linear model to predict the number of ride-related injuries at fixed-site amusement parks in the year 2010. First thing we need to do is think about what is the value of t. So take 2010, the year they're asking about, subtract the starting year, which was 2000, and you get t equals 10. And then we can make the prediction by bringing the graph back in. So on the graph, if I go to t equals 10, pick a different color, and then I hit the line, and I come across just a little bit below the 1.25 line. So I don't know, maybe we'd guess something like 1.21 or something. Like, it's very hard to get that precisely, but 1.21 seems reasonable. And that would be the value of n, and that's 1,000. And 1,000 injuries. We could write it that way. We could also do the thing I did before, multiply by 1,000, which would move the decimal 3 spots to the right. So 121, and then just add a 0 for that last move. Injuries. So 1,210 injuries is our prediction. So now compute the error in the estimation for 2010. So this isn't something we can normally do. However, we happen to know what it was in 2010. It was 1.3 thousand. So the difference between the 1.3, which is reality, and the 1.21, which we predicted, would be our estimation error. And if we look down the page, we'll see that when you're calculating estimation error, the order you do it in is the actual value minus the estimated value. So I'm going to do that. So E is the actual value, which from our chart for 2010 was 1.3, minus our predicted value, which we got from our graph, 1.21, which is 0.09 for the difference. But again, that's 1,000 injuries. So multiply by 1,000, moves the decimal over 3 spots, which would be 90 injuries. So the error, or the difference between our prediction from the model and the truth for what happened in that year was 90 injuries. Seems like pretty close, decent estimate. And then let's see what they have for us in Part H. Use your linear model to predict the number of ride-related injuries at fixed-site amusement parks in the year 2028 and discuss that. So first of all, got to figure out T. So that would be 2028 minus the starting year of 2000, which is T equals 28. And then we want to put that into our graph. And we run into a pretty big problem there. Because T equals 28 is right here. Normally I'd go up until I hit the graph, but there is no graph up there. So this is going to be pretty rough, but I'm going to do the best I can with this. I'm going to extend that line even further. And then I'm going to think about dropping down until I hit the graph. Now, no good really to go across to see how high that is because I don't have an across here. So I got to just kind of look at that size of a square and try and count about how many I think that is. Maybe 1, 2, 3, maybe 4.5 squares down. So each one of those squares was, let's just see if we went 4.5 up, what that would be, right? 1, 2, 3, 4.5. So that would be somewhere in between 1 and 1.25, but it'd be negative because we were down. And it looks like that's more than half a square maybe, so I'm going to say like negative 1.15. You're going to see in a moment how accurately we get that is not terribly important, but it looks like n is approximately negative 1.15. And then what is that? That's 1,000 injuries. And we could multiply by 1,000, which would move that over 3 spots, negative 1,150 injuries. Now the reason it's not that important that we get that perfectly right is this doesn't make sense. I was already doubting that it would be true that there were 0 injuries in the year 2019. I certainly don't think in the year 2028 we're going to get a negative number of injuries. I don't even know what that would mean. So what we have here is model breakdown. And that's not surprising because we tried to make an estimate that was well outside of the data we were given, and we got an answer that didn't make sense. Even if the answer made sense, I still wouldn't trust it as being right because I know it's a big extrapolation, and big extrapolations often lead to model breakdown. And again, what I mean by big extrapolation is the distance between where our data was and how far over that prediction was really large compared to the range of the data. And the further away you get from the data, the more likely it is that you're going to get a bad prediction. All right, so let's go ahead and run through the steps for calculating error, one of the things they had asked us to do. So make an estimate of the dependent variable using your linear model. So that's the line you drew. And then determine the actual value of the dependent variable by looking at your set of data values, or that chart. So we had to go look for 2010 on the chart and see what was the actual number of injuries. and then your error is just actual value minus estimated value. All right, so in this particular section, we did a lot of stuff with the TI calculator. So I just wanted to note for you guys that there's detailed directions for using the TI graphing calculator in the back of the textbook. And that's true whether you have the hardcover, well, the physical book or the ebook. It's in the back either way. If you look in the table of contents in the front, in section 7, VII, it'll list all the different things it tells you about the calculator, and then those start back at page A1, which is basically the very back of the book. And again, you can find that same content in the ebook by logging into my math lab as well. So if you're stuck on some of these calculator steps, feel free to rewatch the video, but you can also look at a step-by-step list of directions in the back of the book too. So whichever one helps you sort it out, or maybe both. All right, that wraps up section 1.4 and chapter 1.